In this problem, we have a coil that's hooked up to a DC battery and a switch. And if the switch is closed, that could allow current to flow. On the right, we have a similar coil that is hooked up to a resistor. Here we're going to see how changes in the current of one coil could cause changes in the current of the other coil. It's a phenomenon called mutual inductance. So the first thing we want to do is just close the switch. And we want to analyze what's happening at different times. So let's start at t equals 0 when the switch has just been closed. All right, so one thing about coils is coils of wire will resist changes to their current. And so for that reason, current is going to take time to build up in this coil. And we're going to find that even when the switch has just been closed, current will not immediately flow. It'll actually be 0 at the start. Now we can go on to graph the current versus time for both of the coils. The one on the left would be called a primary coil, so I'll label it IP, and this would be a secondary coil, IS. So the current in this setup is going to start off 0, but over time it'll actually approach a maximum. Called I max. That's the largest allowable current. So let's show it at a new state now as well. All right, now we'd like to analyze what happens at a later time. Let's say this is going to be a short time after closing the switch. This could be while current is building up in the primary coil. So at that time, current is going to be flowing. And when current is flowing, that would create a magnetic field according to the right-hand rule. So I just want to close my right hand into a fist where the fingers curl in the direction of current. And then the thumb is going to give us the direction of the magnetic field through that cylinder. So we could have field lines that penetrate through like this, and they can keep going and go right through that second coil. So you can see why there could be an induced current in this secondary coil, because the magnetic field that's going through it is changing. At first, the existing field was 0, and now there is some magnetic field in those loops. But according to Lenz's law, a current will now be induced in this secondary coil in order to cancel the change in magnetic flux that's occurring here. So we'll have an induced magnetic field going the opposite way through that coil. That'll be B induced. Now we'll just want to use the right-hand rule one more time on our secondary coil. Point the thumb of the right hand in the direction that the induced field is pointing. Alright, the curl of the fingers will tell us the induced current direction. Notice that the wrappings of the wire here are a little bit different than they are on the left. That's something to watch out for. So we see here that current is going to flow up that wire and then down this wire. So current flows to the right. In order to explain the whole situation, though, of turning the switch on, we should look at one more case. We should look at what happens a long time after closing the switch. A long time after closing the switch, the current will have reached its maximum value. And the field that's going through will be the strongest that it can be. But the current in that existing B field will be constant at that time, according to what we see here. You see, when the current gets toward its max, it stops changing. But at the beginning, it was changing the most. How can you tell that it's changing the most? By the steepness of the slope here. It means that the current was really rising rapidly. But as time went on and it got closer and closer to that maximum value, it virtually stopped changing. So when it comes to the secondary coil, the flux through the coil it stops changing too. So according to Lenz's law, if there's no change in magnetic flux, then there won't be an induced EMF anymore. And so there won't need to be an induced flux or an induced field anymore. So at that time, the current will approach zero and it'll stop flowing. So this is only a temporary phenomenon that we'll see. When we flip the switch, there'll be this induced current created, but it doesn't last. Eventually, that current in the secondary coil will decay towards zero. So we can answer these questions here. At the instant the switch is closed, current in that resistor of the secondary coil flows to the right. It's not always the case that if the primary current is counterclockwise, then the secondary will be as well. It really depends on many factors, one of them being the orientation of the windings of the coil, so it's always something to look for. After the switch has been closed for several minutes, we'll see that the current in the secondary coil will have stopped. Now, what if we open the switch? Okay, so if we open the switch here, we're going to be causing the existing magnetic field to decrease. And if that happens, then the magnetic flux through that secondary coil will decrease. So in order to compensate for the change, the coil will spring into action, creating its own induced magnetic field that replaces the field that was there before. We can do the right-hand rule on this situation. Point the thumb to the right. Thumb is the direction of the induced field. Fingers will be the direction of the induced current. So the induced current flows this way. That means it's going to come down this wire, and we're going to go to the left through the resistor, the reverse of what it was above. So at the instant the switch is opened, current will flow through the resistor to the left. What will this look like as a graph? Well, if there's resistance in the coil, which there always is some, so the current in the primary coil starts off flowing as normal, but when you open the switch, it'll decay. The current in the secondary will sense that sudden change, so it'll induce a high current in that coil, but this one will also decay as time goes on towards zero. Eventually, there won't be any current in either of the coils.